Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about some very famous telescopes and how they contribute to astronomy. But mostly we're just going to get you familiar with some of the great telescopes. I'll show you some of their websites and what to do to look for. And of course we're going to start with the Hubble Space Telescope, arguably one of the most important telescopes ever to be created in the history of mankind. It's orbiting at about 300 miles above above Earth in a continuous orbit, going around the Earth every 90 minutes or so. And it is one of the most important pride and joy jewels of global science, and its impact on humanity cannot be underestimated. It's one of the most important tools, and if you were going to look back in 200 years from today, probably one of the most significant technological things that's ever been built is the Hubble Space Telescope. So we're just going to give some basic details on it. Yes, it's a big telescope, and they're the websites to go look at. The HubbleSite.org, which is run by a consortium with the Space Telescope Science Institute, as well as the European Space Agency's version, which is www.spacetoLescope.org. And this picture you're seeing was taken by people on a servicing mission as they approached the Hubble Space Telescope or left it in order to just show it over the great deserts of Africa. All right, so the Hubble Space Telescope here is being shown to be either captured or released. I believe it's being released by the space shuttle orbiters. And what they do is they just saddle right up to it in orbit, and the arm would go out and grab it. Basically, you're just going to, as this Hubble Space Telescope orbits the Earth, the space shuttle did 5 different servicing missions, one launch, and then 5 missions to service the Hubble Space Telescope. And so all you do to in order to service it is simply fly just as fast as it does, or orbit exactly next to it, and then go right up to it really slowly and latch on, and then you're together. Both of these machines are extraordinarily massive, so your relative speeds have to be very slow, or else you'll twist and torque and nothing will ever happen, because momentum still works even though you're flying really fast and seem to be motionless with respect to each other. All right, so some basics about the Hubble Space Telescope. It's basically a Cassegrain, an elementary Cassegrain type design. There's a big 2.5, roughly 2.4 meter mirror. That's the primary mirror, and that reflects onto the secondary mirror, which then goes back down through the hole in the back of the primary mirror. And all the instruments lie behind the primary mirror. So the Hubble Space Telescope has a big cover for it, and that cover just closes if there's problems or if you just want to or end on flight. And the solar panels provide all the power to it. So there's a number of guidance sensors and a number of guidance small telescopes that track it and keep it aligned as it's moving around, and gyroscopes keep it aligned as well. So all of the instruments inside of it, and there's numerous detectors inside of it that can pick off the light as it's coming through. So let's go look at the actual the space telescope itself. So if we go to Hubble site, which is www.hubblesite.org, which is run by NASA, you can look and see all sorts of interesting things when it was launched in 1990, the servicing missions, learn more about it, where it's orbiting in space. You can look at the pictures of the mirrors, its history, all about how it's built, what pieces of the spacecraft exist. So I would suggest go take a look, because Hubble site has also some of the most amazing images that you'll ever see. And these images are pictures that are taken by the telescope and then constructed by a post facto, and because they all come out black and white through filters. So it's not like it takes a color picture. It again takes a series of filtered images, and all the color images are combined together. So you can go and just take a look at your favorite picture, and just for fun and enjoyment, let's go take a look at, say, this one, which is of a galaxy, NGC 1015. The release date was February of 2018, and we can see a nice, beautiful image coming from it. It's just absolutely gorgeous, and the imagery that you can see coming off it is astonishing. The detail of the Hubble Space Telescope cannot be underestimated, and let me show you exactly what that means. So first we'll go back and say there's also really some cool videos that tell you some things about the Hubble Space Telescope and also things that have been observed with it. There's also some amazing stuff about some things that were good friend of mine, Frank Summers at Space Telescope Science Institute, did some fly-throughs and fly-throughs meaning taking images taken by the Hubble Space Telescope and rendered them in 3D. And so let's go take a look at some of the more interesting aspects of what we mean by the benefit of Hubble Space Telescope. Well, it's in orbit. And because it's in orbit, it doesn't suffer from all of the effects of the atmosphere. And that was the main drive for getting this telescope up in space to begin with. So let's actually go back to the beginning. I'm going to kick out of this a little bit. Boom, boom. So there it is. It's up in orbit above the Earth's atmosphere, which dims the light and causes atmospheric seeing because clouds get in the way, rain gets in the way, and that just doesn't happen with Hubble. So it's an incredibly valuable piece of machinery. So how does it get the information down? Well, when the Hubble Space Telescope takes the image, it doesn't directly broadcast it. It sends the data by radio over to, say, some tracking and data relay satellites. And then those satellites store the data and then send them down to ground stations at various locations, specifically at White Sands Missile Range down outside of New Mexico. And then that data is then transferred over by wire over to the Goddard Space Flight Center in Greenbelt in Maryland. And right over there next to Goddard is the Space Telescope Science Institute in Baltimore, where all of the computing facilities for it live and where the data is stored. And the neat thing about the Hubble Space Telescope is that all the data that you see is available to you, and you can actually go download it at the Hubble Legacy Archive website. So you can go play with the data, because that's one of the reasons for it is that after researchers have done their duty with it, that gets put up on the website. All right, so let's see what we have. What's so important about this? All right, so the resolution is the key. The clarity of the resolution is amazing. So on the left-hand side of this image is from the Palomar Sky Survey. The Palomar Sky Survey was done in the early part of the 20th century, as in the 40s and 50s, and the goal of this was to take a photographic survey of the sky. And the image on the left is about a 1 degree by 1 degree image in the red. I believe this is a red image of specifically NGC 403839, a pair of interacting galaxies called the antennae. And so we can see that there's a bunch of stars in there, and there's this fuzzy sort of antennae thing. And at long, deep exposures, such as taken by the Palomar Observatory, it's a really pretty image. And you go, wow, what is that thing? So I want to see that really close up. So let's see what we can do with the Hubble Space Telescope. On the right-hand side is the core area, the two interacting cores of the antennae taken by Hubble. And so let's go zoom in a bit. Now, when the black and white image on the left, that's a 60 by 60 arc minute or 1 degree image. So 1 degree on a side, which is approximately the same as your thumbnail held at arm's length. So that the antennae in the sky, if you could see them, because they're pretty dim and extraordinarily faint, would be about the same size as one of the large Mare in the moon. All right, so if we zoom in and only look at the inner 5 by 5 arc minutes, or 60 over 5 is about 1/12 of a degree. So that's a very, very tiny amount. So 1/12 of a degree, or 5 by 5 arc minutes. We can see that the photographic survey doesn't have a lot of resolution. We can't see really fine features. We can see there's some bright specks on the left. There's some fuzziness as a result of the photographic image, but it's really unclear. And that kind of fly sort of thing was just a piece of dust on the photograph as it was taken. And so that's all there is to it. You got this piece of dust on there. And the same image, 5 degrees by, well, actually a little tighter than that, is on the right by the Hubble Space Telescope. So we can see that the photographic survey, which was done on the ground under pristine conditions, when there wasn't much light pollution, and had all the time that you needed to take in order to take these amazing images on the ground. We see on the right-hand side the details that the Hubble Space Telescope is able to pick out. And so looking really carefully, you see the bright spots are resolved into other things. So let's zoom out even further and go even to the inner 2 by 2 arc minutes. So the square on the upper right is 2 by 2 arc minutes, which is about the same size as a small crater on the moon, or at least a relatively large crater on the moon, because the moon is about a half a degree or 30 arc minutes across. So this would be a large crater on the moon, such as the crater Tycho, would be the size of the black and white square in the upper left. So then we look at that same dimension image. I cut it down so it's the same dimension of image on the right by the Hubble Space Telescope, and we can see all sorts of details. The details that certainly look like bright spots where it could have been some sort of active formation are certainly borne out. The colors jump out, the details jump out, and that's because of the extraordinary resolution of being above the Earth's atmosphere. We can see the dark dust lanes, we can see the pink glow of hydrogen gas, we can make out enormous star clusters, we can see the core of the galaxy and see it distinguished from the star clusters around it. And so we also even see in the fringes of the image, on the upper right and lower right of the image, we see extraordinarily distant galaxies which do not show up inside of the digital sky survey. Those distant galaxies are extraordinarily far objects, many, many, many hundreds of millions of light years away. And so the Hubble Space Telescope, with its details, allows us to see actual processes as they're going. It's not just about being able to see colors or pretty pictures, it's about being able to detail processes and notice the physics of it. Now remember, a galaxy is so incredibly large that you're not going to see anything move. However, you can actually detect, or at least posit what the flow should be in this kind of thing, and it helps you study exactly what this object, these interacting galaxies are like. So this tells us that the Hubble Space Telescope's ability to resolve objects is incredible and unparalleled. And that's its main advantage, and that's why it had 5 servicing missions. And even after the Challenger disaster, it was determined, and after the Columbia disaster, it was determined that yes, there would be a final servicing mission to the Hubble Space Telescope to keep it aloft for at least another 5 to 10 years, while the James Webb Space Telescope gets ready. Well, so the Hubble Space Telescope is one of the most important space-based observatories because of its ability to get close. It's very difficult to actually put things in space. So it's much easier and much more economical to actually put observatories on the ground. And the vast majority of all science work is from observatories on the ground. And this is a series of major research observatories on the Big Island, the summit of the Big Island in Mauna Kea, Hawaii. And we see a series of telescopes: the Keck Observatory, the Subaru Telescope, NASA's Infrared Telescope, the Gemini North, the CFAHT telescope, lots of little telescopes. And the reason is that on the top of this mountain, it's incredibly clear skies. You're above almost all of the clouds, above everything. It hardly ever rains there, and you can certainly see that the ground looks dry because there's no plant life at the top of the mountain. I think it's 15,000 feet. And so that's high enough that you're above all the moisture, you're above almost all the clouds, and it's a perfect location because the trade winds don't actually bring in huge numbers of storms. However, at the time of this recording, at the end of May of 2018, there's a massive volcano going off, so I'm certain that all research actions at Hawaii are currently off, just because, well, there's a volcano erupting. In any event, the observatories there benefit from high altitude because they're above most of the atmosphere, and the clear and steady skies that normally abound at Mauna Kea are there. So let's take a look at a few of the telescopes at Mauna Kea. And the Keck Observatory, and the images that you're going to see here come from the Keck Observatory website, is one of the most important observatories at that top. And we can see the clouds in the distance, and they're below the observatory. So you can see that, yeah, that's a little bit of a cloudy sky, but you can definitely see that you're above most of the clouds. And you can see the 2 telescopes inside of the pair observatories. The original goal was to be able to do optical interferometry or binocular view, but not like binocular for 3D view, but interferometric view, so you get the effect of having a much larger observatory. So those 2 telescopes are identical in build, and that was the purpose of them, but it's extremely expensive and time-consuming in order to run it that way, so it's seldom done. Anyway, so let's take a look at the two telescopes. They sit at about 13,000 feet above sea level, and they're 10-meter telescopes, which means the diameter of the two telescopes is 10 meters. So let's take a look back there again. And so we see that these domes are about 30 meters or over 100 feet, more like 125 feet across. And you can see there's little cars in the background, and those cars show you dimension and scale, because big truck couldn't even fit a big truck across the mirrors. So the mirrors are actually segmented. They're not solid mirrors. Well, the segments are solid, but it's not one big mirror. Making them in these honeycomb patterns actually does the trick for it. So the light shines off the mirror. The main primary mirror, which is in segments, that goes to a secondary, and then that goes to a tertiary mirror, which then shoves it out to the side to what's called a Coude focus or a Naismith focus, and that allows and you can put you don't have to have the instruments for imaging or for doing spectroscopy on the telescope. You simply bounce it around a whole bunch of other mirrors and then send it down into a room where the data is going. So this is what the telescope looks like close up. Again, this image is from the Keck Observatory website itself, and we can see that the mirror in the center is the 36 segments, and we see the tertiary mirror, which has some baffles around it, and the hole to the side goes off to the Coude focus, which then goes down into the data area. And it's held aloft and the secondary mirror is held aloft by a spindly, rigid structure, so that the secondary mirror simply does not move no matter what the orientation of the telescope is. And there's another view of the observatory where we can see the secondary mirror in reflection. So you see all the hexagonal shapes. Those are the primary mirror segments. We see the tertiary mirror inside the black baffle in the middle, and then we see a hexagonal sort of thing that's kind of off center, and it's to the right of the frame, which contains the secondary mirror. All right, so then that particular observatory has done amazing studies. One of the more important studies that it's done has been used for us to look at the center of the galaxy, and I'll show you that in a bit. Another important telescope for observing is the Gemini North. Now, Gemini North is the north version of the telescope. There's another identical telescope to it in the southern hemisphere, Gemini South, that's in Chile. And these two telescopes are the exact same, the same specs. And what's neat about this is that you can get an interferometric view across from two things across from a quarter of the diameter of the Earth. And that was the plan for it. And so if you have something, you can then have a very large baseline array and see if there's any kind of views from that. So the Gemini Observatory on the right-hand side, which is the silvered dome, the larger silvered dome, that's the one that has an enormous telescope in it. And here's the view of the Gemini North. And this comes from the Gemini Group. It's a very large telescope as well. It's not as large as Keck. And then if we zoom down to a place that I know very well, which is in southern Arizona. If we go down to Tucson, Arizona, which we see in the distance there, we can go to Kitt Peak Observatory. And Kitt Peak National Observatory is in southern Arizona. We can see the clear skies overhead and the starry sky. And I have friends who go and observe there on the 2-meter class mirror that's at the top there. There's also a solar observatory there. Lots of little telescopes. It's a beautiful place to go observing. And a good friend of mine goes and uses that telescope all the time for his studies of star clusters and the planets. So Kitt Peak National Observatory is someplace you can actually go and visit and go on tours. And in fact, some of the smaller telescopes, you can actually book time on them as an amateur if you wish. And this comes from the National Optical Astronomical Observatory website, or NOAO website, and that's the administration of the Kitt Peak National Observatory. Now, if we then go to another facility owned by NOAO, which is the SarahtoLolo International Observatory, NOAO is one of the groups that's involved in administering this, and SarahtoLolo is down in Chile, in an extraordinarily high altitude in the southern hemisphere, at I think it's about 14,000 feet. And these telescopes, they're incredibly important for observing southern hemisphere objects. But Chile and the Chilean desert just doesn't get any rain at all. It hasn't got it for thousands of years, and it's perfectly situated way up high in the mountains. And the Chilean government has bent over backwards to try to help these observatories out into the southern hemisphere, and it's a pride. It's one of the elements of great pride of the Chilean Observatory, and kids in schools go on up and visit these things occasionally, and they consider astronomy one of the key things that gets taught in grade school. So that's SarahtoLolo, which is partly administered by the National Optical Astronomical Observatory in the United States. Now we can go to the European Southern Observatory, and ESO is run by the European, it's a consortium of universities and institutions that is called the European Southern Observatory. And they've got a number of amazing facilities, and one of the more amazing ones is the VLT, or the Very Large Telescope in Atacama, the Atacama Desert in Chile. And you can see from this helicopter drone view that it's really out in the middle of nowhere. The Atacama Desert really has nothing going on. There's literally nothing out there. It's just, there's almost no plant life to speak of. I think the only plant life is inside the rocks themselves. And so the VLT has amazing views of the night sky, and especially of the center of the Milky Way. And these pictures, of course, are credited to the European Southern Observatory. And we can see that the dark, dark, dark skies, even with this camera view, which is just a wide-angle lens using a telephoto, just a DSLR camera, can show amazing views. And we see above to the left of the observatory, that's the belt of Orion and Barnard's Loop going around it. And we can see the band of the Milky Way in the sky quite prominently. And so these observatories have an unparalleled view, and the 4 telescopes can all be pointed in the same direction or used independently. And there's another view of it from the distance. And there's one of the telescopes inside its frame. These are massive, massive scopes, and they're like huge toys to be played with, if you wish to consider it that way. These telescopes, you have to really be careful, because you don't want any water dripping inside these things, so they can only be opened if there's no moisture at all inside there. And you can see they have all sorts of baffles to try to get rid of moisture and keep the damp and get rid of dust and keep airflow going through that, so that the air temperature inside the dome exactly equals the air temperature and humidity outside the dome. That's critical because you can get a microclimate inside these domes. The domes are there for protection, but really they hinder a lot of things, because if you can have different air quality inside the dome and outside, even though the hole is wide open, and that can affect the viewing of the telescope. All right, so the VLT is an incredibly large series of telescopes, and we'll go down and check out their website in a little bit to look at the specs. But you can see they're massive scopes that are on the order of many meters in diameter. So what's the reason for all this stuff? What do we do? High resolution astronomy, what the goal is, if you put a telescope on a mountaintop or deserts, you get above all the atmosphere, you get away from moisture, which causes clouds, and that breaks up seeing. Because if you go out on a cloudy night or even a humid night, it looks kind of foggy and the stars aren't very good. So if you want to, and that makes bad seeing. So no matter what you do, even if you put a telescope on a mountain or up in the deepest desert on top of the tallest mountain, you'll want to put them in space. Or if you put them in space, the thing is that you can actually mirror, or at least use specific kinds of optics in order to approximate what you get in space. So remember we talked last time about the nature of seeing. We have a diffraction limited seeing, and if you're in space you can get that. But on the ground, you can't because of seeing, because of the distortion due to the atmosphere. So what do? Use adaptive optics. And this, again, is from European Southern Observatory, and Yuri Beletsky took this wonderful image of a laser guide that's being shot at the center of the Milky Way in order to take pictures of or try to image the center of the Milky Way in infrared. But that laser actually serves an incredibly important purpose. It's not like it's shooting at the black hole in the center of the Milky Way. Its goal is to create a fake star in the sky. And that fake star, we know where it is, and it's going about 60 or so, it goes about 20 or so miles up, and gets to the top of the atmosphere, reflects off the molecules in the top of the atmosphere, and it can be used as a fake guide star. And that fake guide star is an illuminated patch of sky that's just off to the side of the target that you're actually looking at. And what you do is you look at how that fake guide star flickers, and that guide star is the only effect that it has is it's the atmosphere effect. Now, you want to reduce the effect of the atmosphere because the star is coming from outside of the atmosphere, go through the atmosphere. And so the light coming from, say, this image, which would be coming from the center of the Milky Way, it has to come from the center of the Milky Way and pass through the atmosphere. And so does the laser, but the laser light goes up through the atmosphere and bounces off the Earth's atmosphere and comes back down to the telescope. And so that can be then that we can take the effect of the twinkling of the atmosphere out with special instrumentation called adaptive optics. And so adaptive optics can be used in the following way. And these things are done by the Keck Observatory group again. And there's a group at UCLA that works on the Galactic Center. That's Andrea Getz's group at UCLA. And she uses the adaptive optics, she and her group use the adaptive optics to try to study in infrared the center of the Milky Way. Without adaptive optics, meaning without accounting for or using some tool that like a laser guide star that flickers, that you know exactly how it flickers because you observe it, and to remove that effect, you get the blurry image on the left. And it's a pretty darn good image of the center of the Milky Way without adaptive optics. But when you turn on the adaptive optics, you get the thing at the right. Notice the diffraction of the bright star in the upper right on the adaptive optics group. It has a hexagonal shape. That's because the mirror of the Keck Observatory is a hexagonal shape. Those hexagonal shapes then become the diffraction pattern of the stars in the sky. And Sagittarius A star is the thing that's being pointed to in the center, and that actually is not, there's not a little bright, it seems to be a little bright point, but that's actually the center of the Milky Way, and somewhere right where that arrow is, there's the dynamic center of all those stars in the sky that we see in this image. And the dynamic center, especially the faint ones, because they're so distant, those faint stars, they're faint because of their distance, are orbiting something that's truly massive, and that we can actually study the motions of these stars, and that's what Andrea Getz's group has done at UCLA, and it's an amazing, amazing thing they're able to do. All right, so this is the sum of one of the things they did, and you can compare and contrast between with the adaptive optics on and with it off. And the little plus that's in the center, that's the location of the center of the Milky Way. And again, this is from the UCLA Galactic Center group, which I'll show you their website in a bit. All right, so how does adaptive optics work? So let's actually take a look, shall we? Hopefully the little video is running, and this is courtesy of the Gemini Observatory because they're the ones who created this little video. So we'll take the Gemini Observatory, the light bounces off the primary mirror, goes off to the secondary mirror, goes down through the hole in the primary mirror, and it doesn't go directly into the instrumentation. It does the following thing. Now you got to have a computer hook up to the thing. It goes down through, reflects off a secondary mirror, bounces off a few things, and finally gets to a detector. Now, before it gets to the red path, we want to actually distort the view of the picture. So it comes in these kind of waggly pancakes, and the waggly pancakes have the distortion due to the atmosphere. But if you then have a feedback loop, you can actually use the feedback loop to distort the little tiny mirror and get rid of effects of the seeing. So let's go back and take a look at that again real quick. So I'm going to try to pause it, and then there's the little tiny square feedbacky things. You can see the incoming pancakes are all wiggly, and then we use adaptive optics to shape the mirror coming out. And we see that in the first reflection reflects it off of a half silvered mirror, so we lose some of the light to go to a detector that then quickly goes back and reshapes the mirror that it's reflecting off of to accommodate the shape of the light that has been how it's been distorted by the Earth's atmosphere. And so this can be done if you have a star of known brightness in the field, and that star can be a guide star, a laser guide star. So that's what's done. So you have the adaptive optics then distorts this tiny mirror just a little bit in order to show that tiny mirror on the side gets those little bitty pistons inside the mirror shape it just by fractions of a millimeter. These aren't big changes, but they're just enough, and they have to be done extraordinarily rapidly in order to accommodate the twinkling of the Earth's atmosphere. So the mirror can be deformed slightly by these little tiny things, and then it clears up the image amazingly. And that's the goal of adaptive optics, is to actually clear up the image. And Gemini Observatory is run by the National Science Foundation as well as the Aura Consortium. High-resolution astronomy. The goal is we use either really big telescopes, get them up on top of mountains, or get them into space so that we can do amazing resolution, such as we've seen with the Hubble Space Telescope. And that is the goal of high-resolution astronomy, is to be able to see extraordinarily detailed images such as these of the antennae. All right, so where can you go to actually look at these things? The Observatory.org, which shows you all of these things and talks about the nature of the telescopes. You can see the observatories themselves, pictures that have been taken using them, as well as pictures of the observatory, as well as current research and news that's happening at the Keck Observatory. Some amazing things happen here. Of course, since it's May 17th, the observatory is, of course, having its difficulties as a result. And that's what's been going on there. Astronomy gets talked about up there and at all sorts of locations, and we have nice news coming out of there. But if you just go to the news and videos, let's go look at science news or events and photos of the location. We can zoom down through and take a peek at some of the fun stuff that they're looking at. So, like the roadmap for planet hunting, Keck Observatory has been used to actually verify planets around other stars. So that NOAO, which is noao.edu, has a series of things. There's a visitor center at Kitt Peak National Observatory, which you really should go see if you get a chance. The Large Synoptic Survey Telescope is about to be built. It's under construction, and that's going to be down in Chile as well. There's the SarahtoLolo Observatory, which NOAO is part of, and Kitt Peak National Observatory down in Tucson. So Kitt Peak is someplace you really should go visit if you ever get a chance to go into a dark sky. CTIO has a 4-meter scope, a 1.5-meter scope, and another meter size scope down in Chile. They have lots of things for education and public outreach. So if you want to learn things about them, they have beautiful image galleries, and I invite you to go take a look, because the images that you find here appear in prominent places, such as Astronomy Picture of the Day, and sometimes they even appear in national news media. So if we go look at galaxies, we have all sorts of cool thumbnails of pictures that were taken there, say M33, the Triangulum galaxy. And so NOAO is a national treasure, and you should go take a look at their website. The next one is the European Southern Observatory, and they have a number of instruments and telescopes. The Palomar Observatory, which is the VLT, the 4 8-meter telescopes. They can be used individually or used as a large collection. They also have an observatory at La Silla, which is a 3.5-meter scope. The Apex Atacama Pathfinder exhibit, which is Apex. But one of the more interesting ones is the ALMA array, which is a sub-millimeter array, which is light that is in the microwave wavelengths, and that has to be at extraordinarily high altitude in order to actually look at them. So each of these 12-meter radio telescopes are out in high deserts, and they put themselves together to make amazing images. And the goal with the ALMA array is, let's just take a look at that real quick, because we're going to eventually get to it. See, the ALMA array has a number of amazing things that go with it. Most notably, it has the ability to see the science that it gets is with the cool universe, molecular gas and dust, and looking at the formation of there's the antennae again. So let's take a look. The antennae through the ALMA array. And so we see the Hubble Space Telescope and the Hubble image in the background, but we see, if we look closely, we see the ALMA array, which shows the cooled gas which surrounds and goes through the entire thing, the entire area. So understanding the physics can be done in multiple wavelengths. We can look in visible light, and now we can look in microwave light. And the antennae were one of the prime targets for the ALMA array when it came online. Fascinatingly enough, the European Southern Observatory is trying to build a gargantuan observatory called the Extremely Large Telescope, which would be a 50-meter scope, 39-meter primary mirror, which is just insanely large. They want to build it. In the Southern Observatory down in Atacama Desert, because it's big. The primary mirror would be enormous, and the goal would be to actually try to get the faintest objects, try to see the most faint objects around. So I would just go take a look in the images that are associated with it. One of the nice things I like about it is they have a top 100, which is a lot of fun. You can actually build an entire astronomy course on the top 100 images that were taken by the European Southern Observatory. Next, and I promise you this, which is the UCLA Galactic Center group, which is Andrew Getz's group, which has used these observatories, which has used the Keck Observatory to actually map the movement of individual stars around the center of the Milky Way, which is an amazing, amazing accomplishment. So I would really invite you to go check that out. But this is what's Andrew Getz's group is known for this amazing, amazing work. And they have some amazing public outreach. Their news and science, what is a black hole, what are the telescopes they use, what adaptive optics is, and some of the images and the high resolution images that they've taken. And that's where they come. That's where many of the images that I used on this video were from this website. So I wish you well, and I want you to have happy dark evenings, and hopefully you'll be able to go on outside and appreciate the sky in a different way after listening to this. And hopefully you'll get a chance to go and take a peek at all of these amazing, amazing observatories, the Keck Observatory, the European Southern Observatory, the NOAO, and how to actually go to Southern Observatory as a tourist. You can actually go there. You can have some fun by going all the way down there. Lots of fun things to do. And so we'll talk more about telescopes next time. See you soon.